Alright, so today we're going to go ahead and start the next chapter, which is harmonic oscillation. Particularly, we're going to first look at the first section, which is Hooke's law. But to make this a little bit easier, we're going to go ahead and restrict ourselves to one-dimensional motion. So, as we talked about when we talked about with energy, is anytime I have an equilibrium position, or more importantly, a stable equilibrium position, what we know then is that the force at the stable equilibrium position is equal to 0, right? And again, the reason for that is here, if I look at the derivative of the potential at this location, it must be equal to 0, which means that the force then is also equal to 0 at this particular location. So let's go ahead and define this location as our x0. Now, typically what happens then is that as I move to the left, this thing has a force pushing on it back to the right, and as I move to the right, this thing has a force pushing back on it to the left. This type of force is what we call restorative force. Now, in general, this force can be a highly complicated force. It can depend on position, can depend on velocity, it can depend on higher derivatives of the position as well. But for now, let's go ahead and look at only the case where this force is position dependent. Meaning that this force, as I was drawing the force as a function of position, our force then is only dependent on the position. Now, we will look at situations where the force is velocity dependent. So this thing is and can be dependent on the velocity. Those are what we call damped harmonic oscillators. And this thing can also still be constant even if I have a damped harmonic oscillator. So in that case, what has to happen is as this thing is losing energy due to the velocity dependent term, something else has to be adding energy to the system at the same rate at which energy is being dissipated. Typically as this thing is moving, say, through a fluid, the fluid is going to cause it to dissipate energy. So something has to be injecting energy into the system at the same rate as the fluid is dissipating that particular energy. These are what we call driven or forced harmonic oscillators. But for now, let's restrict ourselves to this type of force, so it's only position dependent, and then we'll come back to those other ones later. And also, again, we're going to relax this one-dimensional case and actually come back to it and talk about two-dimension and generalize the higher dimensional. So, now, again, as we talked about when we talked about with potential energy, around this particular potential, or around this equilibrium position, we can always look at a small enough window to make this thing basically quadratic. So what that means is, around this equilibrium position, which we're going to call x0, which I can always call 0, because I can always move my coordinate system to make this thing at the equilibrium position, or at least the origin of my coordinate system, we can look at small perturbations then around this particular equilibrium position. Now, if we do that, then we can Taylor series expand the force just like we Taylor series expanded the potential. So that means that the force acting on our object then is approximately going to be equal to the force at that equilibrium position plus x times then the derivative of the force evaluated at that equilibrium position plus x squared divided by 2 times the second derivative of the force with respect to position evaluated at that equilibrium position plus higher order terms. Goes x cubed. Now, again here, since this is the stable equilibrium position, what we know is that the potential has to be equal to 0, so the force has to be equal to 0, which means this first term is simply equal to 0. And if we assume that we're doing only little tiny small perturbations, which means that x is going to be much, much less than 1, that means we're only going to keep the first order term. Any higher order terms we're just simply going to ignore, because those are going to be subdominant to that first order term, which means our force then will be just approximately equal to x times the first derivative evaluated at that particular position. Now this thing we're going to go ahead and define then as minus k times x, where k then is defined as minus the derivative of the force with respect to the position evaluated at that equilibrium position. Now, again, here, even though we've inserted this negative sign, it implies that this thing is negative, but that's not quite true because, again, the derivative is actually always going to be negative. Because again, as I'm moving to the left, the derivative will be in the opposite direction, which means it will be positive. If I move to the right, then the derivative will be negative. So in this case, no matter what direction I move, this thing will always be negative. So this is negative with a negative, which makes this whole entire thing positive. So this is what we call Hooke's law. So Hooke's law says that the force acting on the system is then equal to negative k times x, where the negative sign is indicative of a restorative force. This means that the force will always bring it back to its equilibrium position. Again, k is usually what we call the spring constant, but it's related to the derivative of the force. And x then is just the distance away from that equilibrium position. So it's either in a positive direction or in a negative direction. Now, even though this thing, again, is only dependent on the position. Again, this could be dependent on velocity, and we're going to see that again when it comes to velocity dependent or damped harmonic oscillation. But again, we'll come back to that later. So, now that we know about Hooke's law, let's now consider a spring mass system and then actually determine what the solution of this system is. So let's do that. So let's look at a simple spring mass system. So let's say here's my spring. This thing has a spring constant of k. I have a mass m. Let's say this thing is moving horizontally. So if I look at a free body diagram of this, here we're going to have the spring force back in this direction. Let's call that F of S for now. This thing has to have an acceleration. So let's say, I don't know, for fun, this is the direction of our acceleration. So let's call this our x direction. So, now, according to Newton's second law then says that the sum of the forces acting on the object must be equal to the mass times the acceleration, which we know is mx double dots. The only force on this is our spring force, so we have minus k times x is then equal to mx double dot. Now let's add this term to this side, so we get 0 then is equal to mx double dot plus k times x, or if we divide both sides then by the mass, we get 0 then is equal to x double dot plus k divided by m times x. So in this case, if we define what's known as the angular frequency as the square root of k divided by m, we can rewrite this then as x double dot plus omega squared times x. So our job then is to solve this simple expression. Now, the way we're going to do that is, so first off, note that this is a second order differential equation. So pretty much most of the things that we've seen in class so far have been first order differential equations. So to solve a second order, we're going to do is we're going to seek a solution where we're going to say that x is proportional to e to the lambda times t. So, if I take a first derivative of this, so if I have an x dot then is going to be proportional to lambda times e to the lambda t. And then x double dot is going to be proportional to lambda squared e to the lambda times t. So basically, all that's going to happen is I'm going to replace this with lambda squared e to the lambda t plus omega squared e to the lambda t. But since this is all equal to 0, I can then divide both sides by the e to the lambda t. So finally, I get what's known as the characteristic equation. And the characteristic equation in this says that 0 is equal to lambda squared plus omega squared. So here, this is going to tell me then the allowed values of lambda. Once I know the allowed values of lambda, then I can solve and put into my solution for my second order differential equation. So here, solving this for lambda simply says that now that lambda squared is equal to minus omega squared, which is then equal to, so this tells me that now lambda is equal to the square root of then -1 plus or minus times then omega. But square root of -1 is simply I, so the solutions for this are plus or minus I times omega. So that means then that x is then proportional to e to the plus or minus I times omega t. Now, we talked about this early in the semester. Anytime I have a second order differential equation, I have to have then what? Two independent constants, because again, I have two constants for every particular one. So here we're going to do is we're going to take both of these two different solutions, simply add them together with two different coefficients. So this says then that x, our solution, is going to be equal to some c1 e to the I omega t plus then c2 e to the minus I omega t. Now, if I take the complex conjugate of this, so x star, that's going to be equal to c1 star e to the minus I omega t plus c2 star e to the I omega t. So, for those of you who haven't seen complex variables before, star is what we call the complex conjugate. What that means is that anything with a complex, when you take its complex conjugate, you get a negative sign. So, for example, if I took 5, right, which is just a number, and I took the complex conjugate of 5, that's simply equal to 5 because 5 is a real variable. But if I had I times 5, then the complex conjugate of I times 5 is then equal to negative I times 5. So complex conjugate simply negates whatever the negative, or whatever the imaginary term happens to be. So in general, any imaginary number, let's call that simply A, can be written in terms of a real part plus an imaginary part, which pretty much means that what? We can work in the complex plane, where the complex plane happens to be a two-dimensional system, where along the horizontal we have the real parts, and along the vertical axis we have the imaginary part. So here, the way I would think about this is that this has A units in the real direction, B units in the imaginary direction. So this thing actually creates a vector where this is A. So the magnitude of A then is then equal to A times A star square rooted, which is then going to be the same thing as A squared plus B squared square rooted. So this is the magnitude then of this vector, which is drawn in a complex plane. So pretty much any complex variable we can think of as a vector in the complex plane, where this first part is actually what it is along the horizontal direction, this is what it is along the vertical direction, where this is the real part, and then this is the imaginary part. Good. Now, x though, since we're working in real space, x has to be a real quantity, which means, based off this discussion, if I took the complex conjugate of x, that has to be the same thing as x, because x must be real. So all we're going to do is simply say that these two things must be equivalent to each other. So x must be equal to x star to then determine how these guys are actually related to each other. So if I set these equal to each other, then I have c1 e to the I omega t plus c2 e to the minus I omega t must then be equal to c2 star e to the I omega t plus c1 star e to the minus I omega t. So I changed the order of that second one just to basically show it a little bit better. But what has to be true is that the coefficients in front of the like exponential terms here have to be equivalent to each other, which tells me that c1 then must be equal to c2 star, and then c2 must be equal to c1 star. So c1 then is equal to the complex conjugate of c2, and c2 is equal to the complex conjugate of c1. So what that tells us then is that since c1 and c2 are actually related via complex conjugations, we actually really only have one coefficient, where that one coefficient is, let's call that c1, is equal to c, which means that c2 then is equal to simply the complex conjugate of c. So putting that together, what that means then is that we can really then write our solution to this second order differential equation as being x then is equal to c e to the I omega t plus c star e to the minus I omega t. So this is our general solution. So this is one way we can write the general solution of our Hooke's law, i.e. of our simple harmonic oscillation. Now, this is, of course, not the only way we can do it. Another way we can do it is we can use what's known as Euler's formula, or Euler's formula says that e to the I theta is equal to cosine of theta plus I sine of theta. Which means in this case, we can rewrite this then as c times cosine of omega t plus I sine of omega t plus c star times cosine of omega t. Now, in this case, cosine stays the same because remember that cosine of a negative angle is the same thing as cosine of that angle. So I'll write that here. So cosine of negative theta is still equal to cosine of theta, but sine of negative an angle is equal to negative sine of that angle. Good. So this becomes then minus I sine of omega t. So from here, all I want to do is put like terms together. So put the two cosine terms together. So this is going to be c plus c star times cosine of omega t. And then here, we're going to get a, so I want to put the I in here. So let's rewrite this then as minus I times, plus I. So there we go. C minus c star times then sine of omega t. Now, turns out that if I add two complex variables together, where I'm simply taking the complex conjugate, so again, if I go back to A, so remember A was equal to A plus IB, which means A star is equal to A minus IB. So if I take A plus A star and add them together, that's simply twice of A, which means that this is equal to twice of the real part of C. Now, if I take A minus A star, then that's going to be what? I times B plus I times B, which is simply equal to what? Twice of I times B. So let's go ahead and write that. So this is then cosine of omega t. So again, if I take A minus A star, that's equal to 2 times I times B, okay, which is then equal to I times 2 times the imaginary part of C. Okay. So let me erase this section, so I can write that here. So this is then going to be, now I get a plus I times I, but I times I is actually negative 1. Twice the imaginary part of C times then sine of omega t. So from here, we can now define this then to be some new coefficient b1 times then cosine of omega t plus some new coefficient b2 times sine of omega t, where b1 then is equal to twice the real part of C, and then b2 is equal to twice the imaginary part of C with a negative sign. So good. So this is the typical way that you've seen it. This is how we wrote it down before when we worked in something like Physics 205. But another way that we wrote it down in Physics 205 was we wrote this in terms of the phase angle. So one way we can do that is we can note that if we take, it's defined as a new variable a, which is defined as the square root of b1 squared plus b2 squared, meaning that we can work in a complex plane. So in this case, we can then say that, let's factor out a 1 over a. So in this case, we can always rewrite then x as being a times b1 over a times cosine of omega t plus b2 over a sine of omega t. But again, if I think about this in the complex plane, so this is then b1 this is then B2, and then A is the magnitude of this vector wrong here. Now, if we introduce this new angle of delta, then we can see that, what, B2 is the same thing as, what, A times sine of delta, and then B1 is the same thing as, what, A times cosine of delta, which means this term here is then going to be the same thing as, what, cosine. So ultimately it's going to be A then times cosine of delta times cosine of omega t plus sine of delta times sine of omega t. But this is the same thing as a double angle formula, so this is actually the same thing then as A times sine of omega t plus delta, which is the same thing as A times cosine of omega t minus delta, where delta in this case would just be the phase angle. So again, this is just telling me where this thing actually starts in its harmonic oscillation. So any one of these three are equivalent to each other. So any one of these three ways that we wrote down X all discuss or represent how this thing actually starts, or its description in terms of position. So that means either we can write X this way, we can write X as then being B1 sine of omega t. Oops, I think I had that cosine before. Cosine of omega t plus B2 sine of omega t, or X is equal to A times cosine of omega t minus delta, which is equal to A times sine of omega t plus delta. So again, any one of these three ways are equivalent. They all tell me exactly the same information. It just depends on how I'm looking at it or how I want to represent it. So this is the way I would write it in complex variables. This one I would write it as a summation of the cosine plus sine. And then here I would write it, again, in terms of a phase angle. But in each one of these, there are two unknown coefficients. Right? So here I would need to know B1, I need to know B2. Here I need to know A, and I need to know delta. So, very good. Now, each one of these, what happens then is that this thing harmonically oscillates, and it harmonically oscillates with a fixed period. So the way we would determine a period is, for example, if I look at this, what has to happen is this system must return back to itself when it has gone through a period, which means what has to be true is that omega t plus omega times the period must be equal to omega t plus 2 pi. So again, if I think about cosine repeats itself after it has gone through 2 pi worth of angle. So that means this omega t cancels with this one. So what I get then is omega t then is equal to simply 2 pi, which means the period then is equal to 2 pi divided by the angular frequency. So again, this is true for any one of these systems, and they all have exactly the same amount of period. Now we talked about when we did energy, the potential energy of this system. But let's go ahead and talk about it again. So the way we would determine the potential energy is to look at the work which is being done by the spring, or we can also think about, if again this is my spring mass system, and I'm trying to pull this thing in this direction by applying a force F to it, I have to counteract then this spring force in the opposite direction. So we can say then is how much work is it that I need to do to move this thing by an amount of x from some initial position x0 to some final position. And let's move this by an amount of dx. So the differential work that I have to do then is equal to negative of the differential work done by the spring, which is then equal to negative of the force of the spring times dx, because again in this case I'm moving in the same direction as the force is being applied. So this is then equal to k times x dx, which means the total amount of work is simply equal to the integral of k times x dx from some initial position to some final position. So this is the same thing then as k, integral x dx, initial to final, which which is the same thing then as k times x squared minus x initial squared, all divided by 2. Now, in this case, since I'm the one doing the work, we know that must be equal to the change in spring potential, which is the same thing as the final spring potential minus the initial spring potential. If I was looking at simply the amount of work done by the spring, again, I wouldn't have this negative sign, so this would be negative, but that must be equal to negative of the change of the spring potential. So basically from here, we can then identify that the spring potential energy then is simply equal to 1/2 kx squared. So this is our spring potential. So now we can look at the energy of the system. So let's look at the energy. Well, using our solution, so let's use the solution that x is equal to, what, a times cosine of omega t minus delta. This tells me that my spring potential energy then is 1/2 k times a squared times cosine squared of omega t minus delta. And then we can look at the potential energy, or sorry, the kinetic energy. So the kinetic energy in this case then will be equal to 1/2 m times x dot squared. So first if I do an x dot, so x dot then is equal to what? Negative omega a times sine of omega t minus delta, which means my kinetic energy then is 1/2 m times omega squared times a, pardon me, times then sine squared of omega t minus delta. But remember that omega squared is equal to k divided by m, so that m is going to cancel, so it's the same thing as 1/2 ka squared sine squared of omega t minus delta. So first things to note is what? If I take these two and I add them for the total energy, then the total energy then is equal to the kinetic energy plus the spring potential energy, which is simply equal to 1/2 ka squared. So in the case of Hooke's law, or at least of one where the force is only position dependent, doesn't depend on the velocity, i.e. is not damped, then the total energy must be constant over all times. Again, something that we saw back in 205. The other thing is that what? Here, what happens then is that the potential energy and the kinetic energy oscillates, which means the total energy oscillates between both the kinetic energy and the potential energy, where these two things are out of phase by 90 degrees. Meaning when this thing is maximum, this thing is 0. When this thing is maximum, this thing is 0. So as it's moving along its trajectory, so when it's at the origin, it has maximum kinetic energy, so 0 potential energy. By the time it reaches its maximum displacement, it then has maximum potential energy but 0 kinetic energy, and then anywhere between it has a summation of the two of those. So the total energy then is simply the sum of these two oscillating terms, where the energy is oscillating between each one. So, finish this up. Let's go ahead and do an example. So, our example is we're going to look at some pendulum. So in this case, we're actually going to look at a physical pendulum. Now, everything we wrote down here had to do with spring mass systems, but the nice thing about Hooke's law, again, is anything that repeats itself, anything that undergoes simple harmonic oscillation, i.e. anything that goes under a repeated pattern over and over and over and over again, all falls under this. The only thing that's different is you're going to replace x with theta or whatever variable that it is that you're looking at. So good. So here we want to find the angular velocity and period of oscillation of a solid sphere of mass m and radius r about a point on its surface. So here is my sphere, and let's take this as our pivot point. So basically, this thing then is going to harmonically oscillate about this particular point. So its center of mass is going to be here. So this is its center of mass. And again, what I want to know is what is the angular velocity as well as, or sorry, not angular velocity, but angular frequency and its period. So we want to know what is omega and what is the period. So good. So first things first, note that the moment of inertia about the center of mass of the sphere is 2/5 mass times the radius of that sphere squared. So this is the radius. But again, our pivot point is not at the center of mass. It is at some point on the surface, which means to move it to the pivot point, we have to use the parallel axis theorem. So remember, the parallel axis theorem says that the moment of inertia at some point P is simply equal to the moment of inertia about the center of mass, plus then mass of the object times the distance d squared we are away from the center of mass. So if this is my object, this is my center of mass, this is my point P, then d then is the distance away from the center of mass. Now in our case, that distance is simply r squared. So for us, moment of inertia about that pivot point is 2/5 mass radius squared, plus then the mass times the radius squared, which is the same thing as what, 7/5 mass times the radius squared. So this is our moment of inertia about this particular point. Now, this is when it's at its equilibrium position, but let's say that we're going to tilt this guy so that it is at a slight angle tilted to the side, so that the center of mass goes over here. So this is going to be our angle of theta. So basically, here, we're still going to have the center of mass, which has a weight pulling down in this direction. Now, this thing is going to cause a torque. So from here, we can look at the torque. So the net torque then is going to be equal to, now the only thing generating a torque on this guy is simply that gravitational force. So here we have the r vector, which points in this direction, which means this is the angle between r vector and him, where our r vector is simply equal to the radius. So this is going to be the radius times the force, which is mg, times sine of the angle between the two. Newton's second law then says that the net torque magnitude must be equal to the moment of inertia times the angular acceleration, which is equal to the second derivative then of that angle. Now note what happens again is that the torque in this case is always pulling it back to equilibrium. So if I pull it on this side, it wants to go back to equilibrium. If I pull it on this side, it wants to go back to equilibrium. So we need a negative sign here, so this becomes minus r mg times sine of the angle is then equal to moment of inertia times then the angular acceleration. So here we're going to pretend that the angle is small. So we're going to say that theta is much, much less than 90 degrees, so that we can use a small angle approximation. So we're going to say sine of theta then is approximately equal to simply theta. So this then is going to become minus r mg theta is equal to 7/5 mr squared times theta double dot. Now, from here, all we have to do now is get it in the same exact form as before, where before we had x double dot plus omega squared times x was equal to 0. So here, x double dot is going to be replaced by theta double dot, and then theta, or x, is going to be replaced by theta. So let's get rid of one of these r's, get rid of the m, and bring all the terms to the other side. So here I get a theta double dot plus, so bring that guy over here, so this becomes 5/7 of g divided by r times theta is then equal to 0. Now again, from before, we had x double dot plus omega squared times x was equal to 0, which means pretty much whatever shows up in front of the theta is the angular frequency squared by definition. So from matching these two, we find that the angular frequency then is 5/7 of g divided by the radius. And again, what we wrote down before, the period then is equal to 2 pi divided by the angular frequency, which is then going to be 2 pi times the square root of 7/5 r divided by g. So this is then the period of the harmonic oscillation for this particular sphere. So next time, we'll take all this and we'll start generalizing now to multiple dimensions. So what happens if this thing is harmonically oscillating in 2 dimensions or 3 dimensions or etc. And then after that, we'll start looking at things like damped harmonic oscillation and force-driven harmonic oscillation.